Hello everyone. So welcome to IT and Gate classes. And today we are going to discuss the questions of signals and system which is asked in the Gate 2024 for the electronics and communication branch. So one by one, I will be discussing the all questions of the signals and system. And let me tell you that in this time, signals and system was having little bit, tricky, or you can say that it is mostly a confused or the controversial questions asked. So there are two questions in which the MTA has been given. So we will discuss all the questions and the reason behind why they have chosen this question as a MTA or they have changed their options. Everything we are going to discuss. So before starting this session, I would like to tell you about the admission for the GATE 2025 and 2026. We have launched the for multiple streams. The courses which we offer is GATE online coaching, Target GATE course, GATE online test series, and distance learning program. And this is the GATE 2024 Electronics and Communication Engineering Signals and System. What was the weightage? So there were total about 10 number of questions were 2 and 4 and the total marks was 10. Okay, so 1 mark question was 2 and 2 mark question was 4, and in this way we have covered the 10 marks through the signals and system, in which the 2 already given 2 marks to all. Now the first question of this is the MCQ based, and that question was: a causal and a stable LTI system with the impulse response h of t produces an output y of t for an input signal x of t. Now we have changed the signal, we have scaled the signal. X of 0.5 t is applied to another causal and stable LTI system with the impulse response h of 0.5 t. Then what is the resulting output? So it is a property based question. So suppose we have one causal and LTI system, stable LTI system, right? And we have another system which is same, identical, but the input is changed. So this is how this signal is x of t given. This is a stable and LTI system, causal and stable LTI system. So I'm just writing only LTI system. Stable and causal, it is already mentioned for both. So this is also LTI system. Now we have output yt. Here we have given input as x of 0.5 t and we are getting yt, let us say y dash t, because the response will change. The response of this first system is h of t and the impulse response for the second system is 0.5 t. Now whenever we give the input x of t to the system, we expect the output is nothing but the convolution of input and the impulse response. Similarly, here also we will expect x dash t is nothing but the convolution of 0.5 t and h 0.5 t. Correct? Now, according to the convolution property, the result is 1 upon a. Okay, suppose if I write the property over here. Now, if we have x of at convolve with h of at, then we expect the output 1 upon mod a x of, it is y of a t. Okay, expect y of a t. Now here if I apply this, this is 1 upon 0.5 and y of the previous output, which is a scaled version of 0.5. So it is 0.5 t. A is 0.5. So 1 upon 0.5 is 2. So 2 into y of 0.5 t. So according to this, the right answer would be option. Very simple property based question. If the system is having the response y of t, which is the convolution of xt and ht, then if you convolve the xat and hat, then the output is also the scaled version of the original output yt, which is y of at, and also there is a change in amplitude, which is 1 upon a. So in this way we get this answer. Now Coming to this second question, question number 24. For a causal discrete LTI system with the transfer function h of z is equal to 2z square plus 3 upon z plus 1 by 3 and z minus 1 by 3, which of the following statement is and are true? The system is stable, the system is minimum phase, the initial value of the impulse response is 2, the final value of the impulse response is 0. So to calculate whether the system is stable or not, in the Z domain, what we have to calculate, we have to see the pole is inside the unit circle or not, right? So here I am writing, for a system to be stable, mod of Z should be less than equal to 1. Right now, in this question, it is given that this h of z is equal to 2z square plus 3 divided by z minus 1 by 3 and z plus 1 by 3. So now, if I calculate the poles, so the poles are z is equal to plus 1 by 3 and z is equal to minus 1 by 3. Here, in both the case, the mod of z is less than equal to 1. Hence, the system is stable. Okay, the system is stable. So, according to this answer will be correct. But here you can see that this is a MSQ type question. So, we have to also check the all other options. The system is minimum phase or not. So, for a minimum phase system, we have to calculate the zeros of the system. So the zeros of this transfer function is 2z square plus 3 equal to 0 and z is equal to minus 3 by 2 root over it, or we can say that this is plus minus j root over 3 by 2. So the value will be coming as greater than 1. So the zeros are lying outside the circle. So system is not minimum phase. System is not minimum phase system. Okay, because the poles are lying outside, zeros are lying outside. Okay, root over 3 by 2 is greater than 1. So that is why it is not possible. Mod of z is greater than 1 here. Now we have to check whether the initial response, or what is initial value theorem, you can say. So if I apply initial value theorem, then it is limit z tends to infinity, h of z is 2 times z square plus 3 divided by z minus 1 by 3 and z plus 1 by 3. So if I take the z square common, then it is 2 plus 3 upon z square divided by 1 minus 1 by 3 z inverse and 1 plus 1 by 3 z inverse, and limit z tends to infinity. So this z tends to infinity, when you put, you will get 2. So the initial value theorem, you are getting the impulse response as 2. So initial value of the impulse response is 2. So that is also correct. Now what about the final value theorem? So final value theorem, if I apply, this is limit z tends to 1, z minus 1, h of z. So limit z tends to 1, z minus 1 and 2z square plus 3 divided by z minus 1 by 3 and z plus 1 by 3. Z tends to 1, so it is giving us the value 0. Z tends to 1 is 0. So the final value theorem, the final value of the impulse response is 0. So these three answers are correct. So right answer for this question will be A, C, and D. Okay, so this is the multiple select question. So these two questions were having no doubt, and this is the clear question that was asked. Now coming to the next question. This question as given as MTA, though this question is a MCQ question, but it is given to MTA. Why? Consider the two continuous time signal x of t and yt as shown in figure. X of t is given as this, and this y of t. X of f denote the Fourier transform of xt. So x of f is Fourier transform of xt, then we have to calculate the Fourier transform of yt. So we want to calculate the Fourier transform of yt in terms of x. That means we have to represent the signal yt in terms of x. So can you represent this signal in terms of y? Can you represent the y in terms of x? So it is very simple. The mistake I will tell you later, but if you suppose see this question in the examination, then definitely what you would have done is you will see that this signal is in the left hand side. You will first invert it and then you will shift it. That is the normal procedure to solve this question. So first of all, I would be drawing this as this one. Okay, just inverse of minus xt. So minus x of t. And what was that? This is minus 1. This is minus 0.5 and this is 0. Right? And this is plus 1 now because I have inverted it. Now, because our signal is in the right hand side, so I will try to shift it. So how much I have to shift it? So I will be shifting it by the 0.5. So if I shift it by 0.5 towards right, then it is minus of x t minus 0.5. So this will become minus 0.5. This is 0 and this is plus 0.5. Okay. This signal is shifted. This signal is shifted. This is the delayed version. Okay. We are delaying it. So we are delaying it. Now, this signal is very much similar to the original signal, but the original signal is starting from minus 2 and ending up to the minus 2. It is 0.5. So what we have to do? We have to scale it because we want to expand it up to the 2. So what we will do now? Our final signal would be like this. Okay, it should be starting from minus 2, ending should be 0.2. So what will be our signal? Minus x t upon 4. Okay, scaled by 4. Okay, scaling by 4. Then you will divide it by 1 by 4. So it will be multiplied and minus 0.5. Okay, when you are scale it this function by 4, then it will be shifted to the minus 2 and it will be shifted to the plus 2. And this is 1. Right? Now, this signal, we can say that it is our yt. So yt is nothing but minus x t by 4 minus 0.5. So this is the original signal. Now we already know that if x of t is having the Fourier transform x of f, then x of t minus t naught, that is the delayed version, is having the Fourier transform e to the power minus j 2 pi f t naught x of f. Okay, and x of at is having the Fourier transform 1 upon a x of f by a. Now here we have to apply the two property together. So always apply the property from the right hand side. So we will apply this towards the right hand side. So that means we will apply first the delay property. So y of f would be minus x of I should write in this way, like delayed version only. Okay? So this is t by 4, right? Let me write in this way because I have to apply in the two different part. So first of all, I am applying this. So when I apply this, it will be minus e to the power minus j 2 pi f, delay is 0.5. Okay, and then x of f. Correct? Now we have to scale it by factor 4. So scale it by factor 4. So actual y of this is y dash f. This is the first step. Now the second step, which is our actual yf, will be minus 1 upon mod a. Mod a is 1 by 4, right? And e to the power minus j, 2 and 0.5 will become 1 pi f by a. F by a. So we have to replace f by a. So that is 1 by 4. Okay, this is in the denominator. A is 1 by 4. So I have to, this is my whole function. This is my whole function. Now I have to replace everywhere f by a. So this is x of f upon a. A is again 1 by 4. Now this is minus 4. This will come in the numerator. E to the power j 4 pi f with minus sign and x of 4f. So according to the two different property, first of all, because whenever there are two operations, you have to apply the property from the right hand side. So from the right hand side, if I come, then I will be first performing the delay operation. So I will be first performing the delay property, and after that I will be performing the scaling property. So when I perform the delay property, I will get this signal in which we have x of f. Now this f should be replaced by f by a. So everywhere where is f, so this is f, this is f, this 2f should be replaced by f by a, and the scaling factor 1 upon mod a will also come. So we will get this. So according to option, minus 4x of 4f e to the power minus j 4 pi f. So this answer should be correct, right? Minus 4 e to the power j 4, right? Yes. So this answer should be correct. But now this is given as MTA. The reason behind that is there is a printing mistake. In this question, in the original gate question also, they have forgot to write minus sign over here. Correct? Because this is in the negative time axis, so this should be minus 0.5. But in the original question, it is given as plus 0.5, which is a printing mistake. And because of that printing mistake, they have marked this question as a MTA. Otherwise, this conceptually it is not correct, but there is a printing mistake. Now coming to the next question number next 48 from the original paper. A continuous time signal x of t is equal to 2 cos 8 pi t plus pi by 3 is sampled at a rate of 15 hertz. The sampled signal is then passed through an LTI system with the impulse response h of t is equal to sine 2 pi t upon pi by t, pi t cos 38 pi t minus cos pi by 2 produces the output x naught t. What is the expression of x naught t? This is the question MCQ, but this question was also given as MTA. Marks to all. Now the reason we will discuss. First of all, simple. If I don't see the options, then how should I approach this question? I have a signal x of t, and I am sampling it by the sampling frequency 15 hertz, and then I am passing it through this particular system. Okay. Now, first of all, whenever we sample any signal, the phase is not going to change our original spectrum, because whenever we sample any signal, we get the replica of the signal. So let me write, if I sample the signal x of t, so for sampling, if I assume that I am doing the ideal sampling, so I will multiply it with the train of impulse. Okay, I will multiply it with the train of impulse. Then I will get the sampled version, XST, according to this. This is the sample signal. Now, because I am multiplying it with the train of impulse, I will get XST is equal to XT multiplied with summation n equal to minus infinite to infinite delta t minus n ts. This is the train of impulse. Now, if I take the Fourier transform, I will get Fs into summation n equal to minus infinity to infinity x of f minus nfs. This is the sampled version of Fourier transform of sample signal. Okay, this is the Fourier transform of the sample signal. So this is first thing that you have to understand. Now this pi by 3 I am ignoring. Ignore the pi by 3. We will consider it in the last. When we get the final answer, we will consider that phase. So our original signal is x of t is 2 cos pi t. Okay. So our signal is x of t is equal to 2 cos 8 pi t. So what is the Fourier transform of this? The Fourier transform of this is delta f minus 4 plus delta f plus 4, right? Now, if I draw it, the impulses we are getting at plus 4 and minus 4. This is the actual signal Fourier transform, minus 4 and plus 4. The amplitude is 1. This is f. Now, when I sample it, I got repeated terms. As I have already discussed, that when you sample it, you will get xs of f is equal to, first of all, you have to multiply with the sampling frequency, and then summation n equal to minus infinity to infinity f minus n fs, right? So here, when you put n equal to 0, x of f, that means you will get this 4 and minus 4, right? This 4 and minus 4, so that is minus 4, and this is 0, this is 4, and this height is 15 because the amplitude is fs and the sampling frequency is 15, right? Now this is for n equal to 0. When I put n equal to 1, okay, when I put n equal to 1, it will be shifted to 15, and 15 plus 4, 19, and 15 minus 4, 11. This we will get. Similarly, in the negative side also we will get like this. Now when we put n equal to 0 and then n equal to 1 and n equal to minus 1 and n equal to 2, when you put n equal to 2, you will get 30. It will be shifted to 30 like this. Okay, see, so value we are getting is, this is shifted to 15, 15 plus 4, 19, 15 minus 4, 11. This is for n equal to 1. In this equation, when you put n equal to 1, this is for n equal to 0. This is for n equal to minus 1. That means minus 15, minus 11, minus 19. This is for n equal to 2. That means it will be shifted to 30. And 30 plus 4, 34, and 30 minus 4 is 26. And it is up to plus infinity and minus infinity. This is your sampled version xs of f. So now up to this point we have got. So this is the question, the sample signal xs of when passed through the LTI system. Now this sample signal you have got, now you are passing it through the LTI system. So can I write like this? This can be written as 2 sinc 2t into cos 38 pi t minus pi by 2, or I can also write 2 sinc 2t sine 38 pi t, correct? Can I write like this? Now, because I am discussing in the frequency domain, so if I take the Fourier transform of this ht, then this Fourier transform of sinc is multiplied with the sine, that means the shifted version of rectangular. Okay, let me write over here. H of t will become now 2 sinc 2t sine 38 pi t. So now what is the Fourier transform of this rectangular? So we know that at sinc t into capital T has the Fourier transform a rectangular f upon t. So if I use this particular property, then according to this, my rectangular pulse will become, the height will be 1, the width is 2. Okay, the width is 2. When you compare, the capital T is 2 here. When you compare, capital T is 2, and then the product should be 2. So that means A should be 1. So this is my rectangular pulse. But this sinc function is multiplied with sine. That means when I take the Fourier transform, okay, when I find the Fourier transform, that Fourier transform will be shifted to the frequency of sine. So what is the frequency of sinusoidal? It is 19. And because it is sinusoidal, there will be a minus sign also. And the amplitude is also divided by 2j. So we know that the Fourier transform of sine is 1 upon 2j delta f minus f naught minus delta f plus f naught. So using this, Okay, using this, if I write, this is the height 1 upon 2j, and this is the value which is shifted to frequency. It is 19, and 19 plus 1 is 20, because this signal, this rectangular pulse is multiplied with sine. So this rectangular pulse is shifted to the frequency of sine. So we will get this. So this is nothing but your h of f. The actual h of f will be this. Okay, and this signal xs of f, which is the sampled version, is passed through the filter which is having the response h of f. So both are in frequency domain. Now you can understand that this filter h of f is a kind of band pass filter which is only allowing the frequency from 18 to 20. So here 18 to 20 we have this pulse, and here it is having this pulse. So we are having only these two impulses that will be passed through the filter. So now I can say that in the frequency domain, x naught f is having only the two terms. Let me draw it separately here. Only 19 hertz signal will be passed. So it is only these two terms. And because this is having the amplitude 1 upon 2j, and this 19 is having the amplitude 15. So we will get 15 into 1 upon 2j. Here we will get 15 into minus 1 upon 2j. So now this is my x naught of f. So how do you write it mathematically? So we will write 15 upon 2j, and because it is inverted, so it is delta f minus which frequency? It is 19. So 19 minus delta f plus 19, because this side is inverted. Negative half is inverted. Now if I take the inverse Fourier transform, okay, so taking the inverse Fourier transform, this x naught t, which is output, is 15, and this is nothing but the sine and 2 pi into 19t, because the frequency is 19. So answer is 15 sine 38 pi t. Correct? Now considering the ignore phase. Okay, now considering the phase which was ignored. Okay, considering the phase which we have ignored in the initial level, which is pi by 3, I guess, plus pi by 3. In the actual signal, in the actual question, this plus pi by 3 is there. So according to this, 15 sine 38 pi t plus pi by 3 should be correct, isn't it? So this should be our correct answer. But now here only you can observe one thing, that cos theta minus 90 is also sine theta. Correct? 90 minus theta or theta minus 90, both are same. Now if I write cos theta, what is sine theta here? In this question, that suppose this is the theta. So sine 38 pi t plus pi by 3. So if I write this, so 38 pi t plus pi by 3, and this can be written as minus pi by 2. So it is cos 38 pi t, and if I solve this, this is 6, and 2 pi minus 3 pi. So we can say that it is cos 38 pi t minus pi by 6. So you can see that there is one more option, which is option C. So both are the same option. Okay, cos 38 pi t plus minus pi by 6. Okay, so A and C both are correct, but the IIT was given only one answer, but then after challenging, they have accept these two, and that's why they have given as marks to all to this question also. So A and C both should be correct, because both are the same representation, right? So you may get this also, you may get this also. So this is the complete procedure. The solution is very simple, but the important thing was to identify the option. Obviously, when we solve like this, we get only option A. So and we will not see the other options now, because we have got the answer correctly by our procedure. So but they have given the answer in that way that there are two options correct. So that is why that was. Now in this question, this was an MSQ. Now there is again the controversy in this question. The radian frequency values for which the discrete time sinusoidal signal x of n a cos omega n plus pi by 3 has a period of 40. So it is given that the period of this signal is 40. And this is a discrete signal, you can see, discrete time signal. So how do we calculate the period of, actually this is the formula for fundamental period, right? So the fundamental period is calculated as n is equal to sigma upon 2 pi upon sigma, okay, where m is integer. Now the period given is 40, so it is not mentioned that it is a fundamental period or a normal period. They both are different. So fundamental period is when first time when it is repeating the signal, and normal period means every 40 seconds they will repeat the signal. So if I consider this 40 as a fundamental period, okay, if I assume 40 as fundamental period, okay, then my n is equal to m into 2 pi by omega, right? So for option A, it is 0.15 pi. Okay, for option A. Now let's check by option. So 0.5, and this pi and pi will get cancelled, and you will get m. This is 200 upon 15. So you will get 40 by 3. Okay, so m is integer. Now m is integer. So you will choose the integer to round off. This means completely cancel. So for m equal to 3, you will get n equal to 40. So that means this answer is correct. Okay, but because this is MSQ, we will try another one. So now let's say option B. This is option A. Now let's check option B. So m into 2 pi upon 0.225 pi. So this pi and pi will get cancelled, and we will get 2 into 1000 upon 225. Okay, so when we solve it, this is 25 nines are and 2400. So it is coming as 80 by n. So if I take m equal to 9, then the period is 80. So which is not correct. So option B is incorrect. Right. Now let's check option C. Option C is 0.3 pi. So n is equal to m into 2 pi upon 0.3 pi. So it is m into 20 upon 3. So again for m equal to 3, n is 20. So this should not be correct. Okay. And for option D, n is equal to 2 pi upon 0.45 pi. So it is 200 upon 45. So we will get 40 by 9. So for m equal to 9, n is 40. So the fundamental period is 40. So these two are correct. Okay, so one answer that IIT has given is A and D. This was given, and that is also correct. You have seen that this is first method. But when we assume that this period is fundamental period, but they have to mention here, if it is fundamental period, then they have to mention, because they have not mentioned, somebody can approach like this also. Okay, this can also be the another approach, that is sigma is equal to 2 pi by capital N into m. This is not the period, fundamental period, na? So we can use directly as a time period. So this is 40 into m. So it is 0.05 into m into pi. Now if I put m equal to 1, I will get the possible frequency 0.05 pi. if I put m equal to suppose 3, then I will get 0.15 pi. 0.15 pi is there. Yes, option A. Okay. Now m equal to, let us suppose 6, then it is 6 into 0.05 into pi, then it is 0.35. So m equal to 0.3 pi. So now it is also matching. Okay, now if I put m equal to 9, then here it is 9 into 0.05 into pi. You can keep putting the value from m1, 2, 3, 4, 5, 6, 7. I am just taking the direct value because I know what is going to come. So 0.45 pi. So 0.45 is there. So if somebody will solve in this way, considering the frequency, the time period, this period as a normal period, not a fundamental period. If you assume normal time period, then it is the procedure to solve this question. And here you are getting 0.15 also, 0.3 also, 0.45 also. But if you assume it as a fundamental period, then you have only A and D. So the IT has changed the answer as A, C, and D. Okay, means they have given both the answers. So those students who have given A and D, they have also got the right answer. And those who marked A, C, D, all the three, they also got the marks for this question. Okay, so the answer was modified from A and D to ACD also. Okay, so these two answers are considered in this particular question. So if it is fundamental period, then only A and D are correct. But because in the question the fundamental word was missing, the answer correct also accepted as A, C, and D. Now we have one last question from the signals. This is the numerical answer type question, and this is very basic question of property based of fundamental DFT. The relation between any n-length sequence x of n and its corresponding n-point discrete Fourier transform x of k is defined as x of k is equal to Fourier transform of x of n. If I take another sequence y of n, which is the 4 times Fourier transform of x of n, then if the sequence is x of n is equal to 1 to 1, 3, then what is y of 0? So actually here you should know one thing. Then when you calculate the discrete Fourier transform of any sequence of discrete Fourier transform, means any sequence is x of n. If you take the discrete Fourier transform of discrete Fourier transform, then you will get n into x of minus n. N into x of minus n. So if you take the discrete Fourier transform of this above, let us say y, let us say z. Okay, let us say z. So this z. Then what you expect? You expect n square x of minus n. Okay. N square x of minus n. N into n is multiplied, and x of minus n into x of minus n will x of minus n only. Means this is the property. Okay. Now what will happen? Because this is now y of n, but we want to calculate y of k. So what is y of k, which is the discrete Fourier transform at k equal to 0? It is summation n equal to 0 to n minus 1 y of n e to the power minus j 2 pi k n upon n. We want to calculate y of 0. That means k is 0. N equal to 0. The length of the sequence is given as 4. So 4 minus 1 y of n e to the power 0. That means summation n equal to 0 to 3 y of n. What is y of n? Y of n is n square x of minus n. So this y of 0 is n square into summation n equal to 0 to 3 x of minus n. So n is 4, so 4 square. And what is the n equal to 0? That means x of 0 plus x of 1. Minus 1 also you can say this is a periodic. It follows the discrete Fourier transform, follows the periodicity. So it will come this only. 4 square means 16. And it is 1 plus, what is the value? 1, 2, 1, 3. 1, 2, 1, 3. So 1, 2, 1, 3. So it is 16 into 7. 1, 1, 2. So 1, 1, 2 will be the right answer for this question. 1, 1. That is the correct question. Numerical answer type, correct question. Okay, so thank you for watching this session. This is the all about the questions of the signal system for the EC. Similarly, the EE and IN also we will discuss. And for more detail, you can contact in this number. And if you want to inquire about any batch specific like Gate 2025 batch, Gate 2026 or distance learning, you can contact in this number and get the detail of the courses. Thank you. Don't forget to subscribe this channel and don't forget to join our other social media platforms.